Now we are going to discuss the laws of thermodynamics. In that, the first one is 0th law of thermodynamics. This 0th law of thermodynamics, it states that when two bodies, capital A and capital B, are separately in thermal equilibrium, with a third body C, say thermometer. Then the bodies A and B are also in thermal equilibrium with each other. This is the thing. When two bodies, capital A and capital B, are separately in thermal equilibrium with a third body C, say thermometer, then the bodies A and B are also in thermal equilibrium with each other. And generally the 0th law of thermodynamics gives the concept of temperature. The first law of thermodynamics, the 0th law of thermodynamics, gives the concept of temperature. Next one is first law of thermodynamics. This first law of thermodynamics states that the heat supplied to a system is equal to the sum of the increase in internal energy and the external work done. So, it states that the heat supplied to a system is equal to the sum of the increase in internal energy and the external work done. And the external work done. Suppose here what you can say is mathematical form. If dq is the heat supplied, comma, du is the increase in internal energy, and dw is the external work done, then from first law of thermodynamics, you can always write the mathematical form dq is equals to du plus dw. This is first law of thermodynamics. It states that the heat supplied to a system is equal to the sum of the increase in internal energy and the external work done. If dQ is the heat supplied, du is the increase in internal energy, and dW is the external work done, then from the first law of thermodynamics, it is given by dQ is equals to du plus dW. Then here, what is the increase in internal energy and what is the external work done? Suppose increase in internal energy. Generally, here the internal energy of a system is equals to the sum of the potential energy and the kinetic energy. Then we know that internal energy is given by standard form U is equals to F by 2 into N RT. Here F is the degrees of freedom. F is the degrees of freedom and N is the number of moles. And here this is the internal energy of the system. Now differentiate both sides. Then what you are going to get? du is equals to F by 2 nr into dt. But we know that gamma is equals to 1 plus 2 by f, where f is the degrees of freedom. From that, 2 by f is equals to gamma minus 1, or f is equals to 2 by gamma minus 1. This is equation 1 and this is equation 2. Now substitute equation 2 in equation 1, then du is given by, in the place of f, 1 by 2 nr dt into f is 2 by gamma minus 1. This 2 gets cancelled. Therefore, this is given by n into r by gamma minus 1 into dt. But r by gamma minus 1 is nothing but Cv. This is nothing but ncv dt. Therefore, the increase in internal energy of the system is always given by ncv dt. This is the standard form, increase in internal energy. Increase in internal energy is given by du is equals to ncv dt. Then come to the other one. What is the external work done? Next one is external work done. What is the external work done? That means when you consider 1 mole of an ideal gas, let us say 1 mole of ideal gas is kept in this one is enclosed. Suppose this is 1 mole of ideal gas is enclosed in a cylindrical vessel provided with a movable piston. Whenever it gets heated, the piston is moved back through an elemental distance dx. If it is moved through an elemental distance dx due to the force exerted by the gas molecules. So, how to find out the formula for this external work done means, consider 1 mole of an ideal gas is enclosed in a cylindrical vessel provided with a movable piston. Of area of cross section capital A. Now, this is the point here. When heat is supplied to the system, then the piston is moved through an elemental distance dx. Hence, the elemental work done is given by dW is equals to force into this way, F into dx. But what is F? From this it is given by F is called PA into dx, or it is P into d. This is the work done when it is moved through an elemental distance dx. This is the formula for the work done. The external work done is given by dW is equals to PD. Once you got the general idea for the increase in internal energy and the external work done, then now we can write this from first law of thermodynamics. The other form you can write dq is equals to du plus dw, or dq is equals to du plus pdv. This also you can write, or dq is equals to du plus nr dt. Different forms. This we can write here because dw can be written as pdv, which is equals to nr dt. But here, whenever you are going to solve the problems based on the first law of thermodynamics, we must use the sign convention. In that, first point is heat supplied. To the system. Then Q is positive. Heat absorbed, otherwise both are same. Second one, heat removed from the system or extracted from the system. Then dQ is negative. This is the sign that we have used. Heat absorbed by the system or heat supplied to the system, then dQ is positive. And third one, work done by the gas is positive. Next one, work done on the gas is negative, or work done by the gas means during the expansion, during the compression, like that also we can say. And increase in internal energy is positive, and decrease in internal energy is negative. So these are the points that we have to remember while solving the problems related to first law of thermodynamics. Once you got the idea of this, now come to the other one. What fraction of total heat is utilized to increase the internal energy, and what fraction of total energy is utilized to do the external work? So, side heading, that is expression, or otherwise you can say fraction of increase in internal energy. What is the fraction of increase in internal? That means it is simply nothing but du by d. Increase in internal energy to the heat supplied is nothing but fraction of increase in internal energy. We know that it is ncv dt by dq is equals to ncp dt. So these gets cancelled. Cv by Cp, which is equals to 1 by gamma. So du by dq is equals to 1 by gamma. And fraction of external work done. Regarding this fraction of external work done, it is nothing but dw by dq, that is pdv by ncp dt, or nr dt by ncp dt. These are gets cancelled. R by cp, which is nothing but cp minus cv by cp, that is 1 minus cv by cp, that is 1 minus 1 by gamma. Therefore, dw by dq is equals to 1 minus 1 by gamma. This is the work done. Fraction of external work done is given by this formula. Once you know that, then how can you adapt to this all? This is du is 1, du by dq is 1 by gamma, dw by dq is 1 minus 1 by gamma. And once you know that, we can calculate the same for a simple table form. We can say that this is serial number, nature of gas, fraction of increase in internal energy, that is du by dq is equals to 1 by gamma. Next one is fractional work done, that is dw by dq 1 minus 1 by gamma. If you observe this, the first one is, if you can see that, if you take for mono atomic gas, we know that for monoatomic gas gamma is equals to 5 by 3. When it's gamma is 5 by 3, this can be written as the fraction of increase in internal is 3 by 5. If you want this in percentage into 100, which becomes 60%. Whereas here this is 1 minus 1 by gamma, this is 2 by 5, which is equals to 40%. Directly we can write the values here. Second one, if you consider diatomic gas, then gamma is equals to 7 by 5. When gamma is 7 by 5, this becomes 5 by 7. This is in terms of percentages, if you can write, nearly it is 72% approximately we are writing. and this is 2 by 7, approximately 28%. And when you consider the triatomic gas, then gamma is equals to 4 by 3. In that case, here, then this is 4 by 3 means 3 by 4, which is equals to 75%, and this is 1 by 4, which is equals to 25%. So, whenever you are asked the problems related to this, sometimes you may be asked what fraction of, what is the fractional increase in the internal energy in case of a monatomic gas, or in case of like that if you are asked, then these are the values straight away. So, by knowing the value of gamma, you can find out fractional increase in internal energy or fractional work done. Or by knowing this, we can also calculate Cp and Cv also. This is the advantage by knowing the value of gamma. That is the ratio of molar specific heats. Then come to the other one. In the application of this first law of thermodynamics, we have heat engines. In that, the first one is heat engine. What is meant by this heat engine? That means it is a device used to convert heat energy into mechanical work done in a cyclic process. So, it is a device used to convert heat energy into mechanical work for a cyclic process. And this is a reversible heat engine also. You have two types of process. One is a reversible process, other one is irreversible process. Reversible process means the process which can retraces its path to come back to its initial state with the small changes is called as the reversible process. And irreversible process means the process which cannot proceed in the reverse direction is called as irreversible process. Now forget about that. Here, that what is heat engine means it is the device used to convert heat energy into mechanical work through a cyclic process. And what are the main parts of this heat engine? That is, the main parts of heat engine. The first one is the source, the second one is the sink, third one is the working substance, and fourth one is insulated stand. These are the four parts, main parts of the heat engine. So first one, if you consider the source, that is, it is a hard body. It is a hard body which maintains a high temperature. T1 Kelvin, having high thermal capacity. It is a hot body which maintains a high temperature T1 Kelvin having high thermal capacity. The side walls and bottom surface are thermally insulated and the top surface is a conducting surface. This is about this. That means if you can see that it is the source if I am taking this is conducting surface and this is insulated. This is the source which maintains T1 Kelvin. So this is about the source. Now it is a hot body which maintains high temperature T1 Kelvin having high thermal capacity. The side walls and bottom surface are thermal insulated and the top surface is a conducting surface. This is for source. Next one is the second one is sink. That is, it is a cold body. It is a cold body which maintains a low temperature T2 Kelvin, which maintains a low temperature T2 Kelvin. Now, the side walls and the bottom surface, the side walls and the bottom surface are thermally insulated and the top surface is a conducting surface. That is what you are going to get here. This is here also. This is the conducting surface. This is sink having T2. This is the sink. It is a cold body which maintains a low temperature T2 Kelvin. The side walls and the bottom surface are thermally insulated and the top surface is a conducting surface. It will be like this. And thereafter you have working substance. ideal gas is used as a working substance. And here what you can say is it is a cylindrical vessel provided with a movable piston. It is a cylindrical vessel provided with a movable piston. The side walls and the piston are thermally insulated. And the bottom surface is a conducting surface. And the bottom surface is a conducting surface. That means, if you can observe this, it is like this. This is working substance. Not only gas, but there might be any other thing that is required here. These are all insulated. And this is a conducting surface. So, an ideal gas is generally used as the working substance, and it is a cylindrical vessel provided with a movable piston. The side walls and the piston are thermally insulated, whereas the bottom surface is a conducting surface. And finally we have another one is insulated stand. An insulated stand is nothing but an insulated stand is an insulated stand function is to allow the working substance to undergo adiabatic process. This is the insulated stand. So, an insulated stand function is to allow the working substance to undergo adiabatic process or adiabatic changes. You can say, instead of writing that adiabatic changes, the purpose of this insulated stand is that, and it will be a slab. An insulated slab is nothing but an insulated stand. Then, what is the working of the heat engine? Working of heat engine. That working of heat engine is, the first thing is here, the working substance first is kept on the source. Whenever it kept on the source, this schematic diagram will be like this. Suppose this is the source. This is the working substance. And this is the sink. Like this. First of all, the working substance is kept on the source. So here what happens, suppose this is already we are given. This is the source and this is the, now on this when you kept the working substance, then what happened, the conductivity takes place between these two. As a result, what happened, it extracts heat Q1 from the source. Q1 heat is absorbed by the working substance from the source, and thereafter work is done by the gas. Let us, W is the work done by the gas, and the remaining or heat is rejected to the sink. This is the basic simple thing. So the working substance extract heat Q1 from the source, does some work, W, and then rejects a huge amount of heat energy to the sink, that is Q2. Therefore, here according to the total heat supplied, Q1 is always equals to Q2 plus W. Therefore, work done is always given by Q1 minus Q2. This is the point. This is the total work done. Then how to find out the efficiency? The efficiency of heat engine. That efficiency means it is nothing but it is the ratio of work done per cycle to the heat absorbed. And generally it is denoted by eta. Therefore, efficiency eta is equals to work done by heat absorbed. Here work done is W, by heat absorbed is Q1. But W is nothing but Q1 minus Q2 by Q1. That's 1 minus Q2 by Q1. Therefore, the efficiency is 1 minus Q2 by Q1. This is the expression for the efficiency of the heat engine. Then how? Once you got the idea of this, what is the Carnot cycle? And this is also expressed in terms of the temperatures. It is also given as 1 minus T2 by T1. That also we can write. But how we got it, we'll discuss later. The T1 and T2. T1 is always be temperature of source. T2 is given by temperature of sink. This is standard that we have to consider. So, efficiency is nothing but work done by heat absorbed. But work done is Q1 minus Q2. Therefore, it is 1 minus Q2 by Q1. That can also be written as 1 minus T2 by T1. And after that, yeah, come to the other point here in this case is given by Carnot cycle. This Carnot cycle is nothing but the reversible heat engine. And here it is a reversible heat engine which is operated between two different temperatures, which is operated between, it is a reversible heat engine which is operated between two different temperatures. And here in cyclic process, it undergoes to isothermal and to adiabatic process. Or adiabatic changes to isothermal and to adiabatic changes then in 4 stages. So what are the points that is related to this one? What is the cyclic process involved in this? Here if you can see that is undergoing like this. Let us say this is the point A, this is the point B, this is the point C, and this is the point D. This undergoes P1, V1, T1. This is undergoing P2, V2, T1. At this point P3, V3, T2. Yeah, P4, V4, T2. And this. This is a cyclic process which involves this is isothermal expansion, this adiabatic expansion, the third one is isothermal compression, and the fourth one is adiabatic compression. In 4 stages, it again comes back to the initial state. So it is a reversible heating which comes back to its initial state. And here, in that first step 1, that is when the working substance is kept on the source, then it extracts a heat Q1 and expands from and expand isothermal and expands isothermally from state A to state A P1 comma V1 comma T1 to the state B P2 comma V2 comma T1. When the working substance is kept on the source, then it extracts a heat Q1 and expands isothermally from state A P1 V1 T1 to the state B P2 V2 T1. Therefore, From first law of thermodynamics, we know that dq is equals to du plus dw. But this is dq is equal to 0 plus dw, because in isothermal process the increase in internal energy is 0. Therefore dq is equals to dw, or otherwise here the heat extract is q1, that is equals to w1, which is nothing but 2.303 nRT log of V2 by V1 to the base 10. This is the first one. This is equation 1. Here, first step 1, what happened is it undergoes the cyclic process. In the first step, it undergoes isothermal process when the working substance is kept on the source. Then it extracts heat Q1 from the source, and then here this is nRT1 because the temperature remains constant. Thereafter, this is the first step. Now step 2. The working substance is removed from the source and kept on the insulated stand. So that it undergoes adiabatic expansion. From state B, P2, V2, T1 to the state C, P3, V3, T2. The working substance is removed from the source and kept on the insulated stand so that it undergoes adiabatic expansion. From state B, P2, V2, T1 to the state C, P3, V3, T2. So the second one is adiabatic expansion. And therefore here what you are going to get from first law of thermodynamics. From first law of thermodynamics, it is given that working is given dq is equals to du plus dw. But in the second case, the heat supplied is 0. Therefore, du plus dw. Therefore, dw is equals to minus du. Therefore, here we can write w2 is equals to minus ncv dt. But this can be written as here cv is nothing but r by gamma minus 1. Therefore, w2 is equals to nr by nr into t2 minus t1 by gamma minus 1. This is, here we can write that cv is equals to r by gamma minus 1. This is the case. Here, in adiabatic process, the exchange of heat becomes 0. Therefore, W2 is equals to nR by gamma minus 1 into T2 minus T1. Thereafter, step 3. Now, the working substance is removed from the insulated stand and kept on the sink at T2 Kelvin. Then so that it rejects a heat Q2 to the sink and undergo, and it compressed isothermally and is compressed isothermally from state C P3 V3 T2 to state D P4 V4 T2. This is the thing that is happened. Thereby what you are going to get here? Again, from first law of thermodynamics, it is given by dq is equals to du plus dw. But here this is heat rejected is Q2, that is equals to, what is du? Du is nothing but 0 plus nr dw. Okay. Therefore, Q2 is equals to nr 2.dw, that is nothing but 2.303 nr T2 into log of V4 by V3 to the base 10. That is the second one we have. Or other, because the heat is rejected, when you apply this is also becomes minus sign, you can write, or Q2 is equals to, you can write this as 2.303 nr T2 log of V3 by V4 to the base 10, because heat is rejected. This is step 3. And step 4. That step 4 is, now the working substance is removed from the sink and kept on the insulated stand. And kept on the insulated stand. So that it expands. So that it's compressed adiabatically from state D to the state, from the state D P4 V4 T2 to the state A P1 V1 T1. This is what you are given. So that it is compressed adiabatically from state D to the state this one. And once you got the idea of this, then from first law of thermodynamics, it is given that dq is equals to du plus dw. Therefore, dq is given by, here again I saw du plus dw you can write, or dw is equals to minus du, or dw is equals to, what you can write here, minus nr or NCV dt. That is dW is equals to minus NR by gamma minus 1, NR by gamma minus 1 into T1 minus T2. Final temperature minus initial temperature. Therefore, dW is equals to minus NR into T1 minus T2 by gamma minus 1. This is a work done in adiabatic. Work done in adiabatic process is given by NR by gamma minus 1. That is NR by gamma minus 1 into T2 minus T1, and that is given by the formula for this. Step 4. And after that, once you got this is the cyclic process, then total work done W is equals to W1 plus W2 plus W3 plus W4, that is given by 2.303 nRT1 log of V2 by V1 to the base E plus NR into T2 minus T1, that can be written as first one T1 minus T2 by gamma minus 1 plus 2.30 minus 2.303 nRT2 log of V3 by V4 to the base E minus NR into T1 minus T2 by gamma minus. These two gets cancelled, therefore this W is equals to, it is given by 2.303 nRT1 log of V2 by V1 to the base E minus 2.303 nRT2 log of V3 by V4 to the, sorry, it is base 10 only. This is what, but this is equivalent to, this is also nothing but Q1 minus Q2. This is equation 1. And once you got this one, the remaining we can easily do it. That is, for adiabatic process. From state B to state C. T1 V1 T1 V2 power gamma minus 1 is equals to T2 V3 power gamma minus 1. Therefore, here we can write this one equation, second equation, from state D to state A. That is nothing but what you given is, that is T2 V4 power gamma minus 1 is equals T1 V1 power gamma minus 1. That is equation number 3. So equation 2 divided with equation 3, T1 V1 power gamma minus 1 by T1 V2 power gamma minus 1 is equals to T2 V3 power gamma minus 1 by T2 V4 power gamma. This and this cancel. Therefore, V1 by V2 is equals to V3 by V4. Therefore, here V1 by V2 can be written as, or V2 by V1 is nothing but This is what you got it here, V3 by V4 or V2 by V1, or otherwise you can write V1 by V2 is equals to V1 by V2 is equals to V3 by this by this, this by this. So this is equation V4 by V3. Therefore, it is V4 by V3. Therefore, V2 by V1 is equals to V3 by V4. That is equation number 4. Therefore, here V2 by V1 and V3 by V4, if you can write here, then substitute equation 4 in equation 1. Then total work done is given by 2.303 nRT1 log of V2 by V1 to the base 10 minus 2.303 nRT2 log of V2 by V1 to the base 10. Therefore, finally, it is given by 2.303 nR T1 minus T2 into log of V2 by V1 to the base 10. Therefore, once you got it, the efficiency of heat engine, it is given by the definition already we are given, eta is equals to work done by heat absorbed, that is 2.303 nR into T1 minus T2 into log of V2 by V1 to the base 10 by 2.303 nR T1 log of V2 by V1 to the, all are gets cancelled here. So eta is given by W by Q1, which is T1 minus T2 by T1, that is 1 minus T2 by T1. Therefore, it is W by Q1 is equals to 1 minus Q2 by Q1 is also equal 1 minus T2 by T1. These are the different forms for the Carnot cycle. This is how we are going to derive the efficiency of the heat engine in terms of two different temperatures, T1 and T2. Thereafter, come to the other one, that is, and this first law of thermodynamics always gives, the first law of thermodynamics gives the law of conservation of energy. Now come to the other one, second law of thermodynamics. Generally, there are so many statements like Kelvin statement, Clashes statement, etc. For all this, only thing that we can say, heat cannot flow from a body at low temperature to a body at higher temperature. Or otherwise you can say that heat cannot flow from a cold body to a hot body unless it is aided by an external source. And it is the direct consequence of entropy. But here there is one point that we can say that here a refrigerator working of a refrigerator. The working of a refrigerator is simply nothing but it is also a heat engine. It is also a heat engine operated in reverse direction. is also called as heat pump. So it is also a heat engine but operate only in the reverse direction. This is also called as the heat pump. Here the basic thing, the working of this, if you can consider, this is the source, this is the working substance, and this is the sink, like this. Source is at T1 Kelvin, sink is at T2 Kelvin. Here it is working in reverse direction. So what happened is that working substance extracts a heat Q2 from the sink, and some work is done on the working substance by an external agent called as the compressor, and the remaining heat is rejected to the source. So the working of this is, again, the working substance extracts a heat Q2 from the sink. Thus, work is done on the substance by an external agent called as a compressor. Here is the compressor we can have like this. That is the external agent, and does some work by the external agent compressor and on the gas, and thereafter a huge amount of heat energy is rejected to the source. Therefore, here also, if you consider that Q2 must be equal to Q2 plus W must be equal to Q1, because the total heat remains constant. Therefore, W is again Q1 minus Q2 only. But here, the point in this case is given by here the performance coefficient. The performance coefficient is given, denoted by beta. The performance coefficient beta is the ratio. It is the ratio of heat absorbed to the work done. The work done for one cycle is called work done for one cycle. Therefore, beta is equals to heat absorbed is Q2 by work done. That is Q2 by Q1 minus Q2. Or this is nothing but T2 by T1 minus T2. This is the formula for the refrigeration. Generally, if you are asked what are the basic differences between the heat engine and the refrigerator, that is, a heat engine is a Carnot cycle. It is a reversible heat engine. And this is also, it is a heat pump like this. Okay. This is some important basic things that are in the thermodynamics. Okay. In the next class, we'll discuss another topic. And if you want any assignment, you can get the assignments through mail ID. If you send your mail ID, I will give the assignments based on the thermodynamics. Okay? Thank you.